Structure of atom. Atom. Electron orbits, electron, neutron, proton, nucleus. Laws of chemical combination. Law of conservation of mass. Law of constant proportion. Dalton's atomic theory. 1808. Discovery of electron. Thomas model of atom. 1898. Ernest Rutherford model of atom. 1917. Rutherford experiment and observation. Preference of gold foil. Drawbacks of Rutherford model. Bohr's model of an atom. Distribution of electron. Discovery of electron, proton, neutron. Comparison of characteristics of electron, proton, neutron. Neutrons. Ion. Symbol of elements. Atomic zone. Atomic number Z. Mass number A. Electronic configuration of first 20 elements. Questionnaire. Isotopes. Isotopes of hydrogen. Isotopes of carbon. Characteristics of isotopes. Questionnaire. Use of isotopes. Isobars. Isobars and their properties. Same chemical properties, different physical properties. Isotones. Atomicity. Mole concept. Questionnaire. Questionnaire. Atoms are building block of matter. Law of chemical combination. Law of conservation of mass. In a chemical reaction, the mass of reactants and products remain constant, given by Lavoisier. Law of constant proportion. Many compounds were composed of two or more elements, and each such compound have the same elements in the same proportion, irrespective of where the compounds came from or where prepared it. Given by Joseph Prout. Dalton's atomic theory. 1808. All matter is made up of invisible particles called atoms, which cannot be created or destroyed. Atoms of the same element have identical mass and physical properties. Compounds are a combination of atoms of two or more elements. All chemical reactions involve the rearrangement of atoms. Discovery of electron. Discovered by J. J. Thomson in 1897. Cathode ray experiment. High voltage cathode negative, anode positive. Cathode ray charged charger plates, battery, magnets. Scale on outside of glass. Thomson's model of an atom proposed in 1898. An atom consists of a positively charged sphere and the electrons are embedded in it. The negative and positive charges are equal in magnitude. So the atom of a whole is electrically neutral. He proposed a model of the atom be similar to that of a Christmas pudding or watermelon. Plum pudding model. 1904. Plum pudding model. Negatively charged particles electrons, positively charged particles negative minus positively plus. The plum pudding model was a model of an atom created by J. J. Thomson. The model describes the atom as a negatively charged particle swimming in a positively charged sea. It got its name because the model resembled the look of a plum pudding. Black, electrons embedded in an atom, and red, positively charged sphere. Ernest Rutherford model of an atom, proposed in 1911. In 1911, he performed the first artificially induced nuclear reaction by conducting experiment in which nitrogen nuclei was bombarded with alpha particles. A few positively charged alpha particles were deflected by small and large angles due to the presence of heavy positive center nucleus. Gold foil detector, beam of particles, radioactive source. Rutherford gold foil experiment. Most alpha particles travel through the foil undeflected. Some alpha particles deflect by small angle. Occasionally, an alpha particle travels back from the foil. Rutherford atomic model. Electrons, nucleus, orbit. Alpha particles, gold atoms, undeflected particles. Few particles rebound, deflected particles. The mass of an atom is due to protons and neutrons. The radius of an atom is 1 lakh times the radius of a nucleus. Rutherford's experiment and observations. Rutherford concluded the model of an atom from the alpha particle scattering experiment as follows. There is a positively charged center in an atom called as a nucleus. Nearly all the mass of an atom resides in the nucleus. The electrons revolve around the nucleus. The size of the nucleus is very small compared to the size of the atom. Orbital electrons negatively charged. Nucleons containing positively charged protons. Preference for gold foil. Gold is incredibly malleable, which means it can be hammered into extremely thin sheets. If the gold were any thicker, if the foil were any thicker, the alpha particles might not have been able to penetrate it. Might not have been able to penetrate it. Backdraws of Rutherford model. The atomic model failed to explain the distribution of electrons around the nucleus and also the stability of atoms. It can be explained further that the revolution of an electron in a circular orbit is so expected to be stable. Any particle in a circular orbit would undergo acceleration, and during acceleration, charged particle would radiate energy. Thus, the revolving electrons would lose energy and finally fall into nucleus. This means that the atoms are highly unstable, which is not true. Gold foil used was about a thousand atoms thick. Thomson's model, Rutherford's model, Bohr's model of atom. Positively charged nucleus, first layer K shell, second layer L shell, third layer M shell, fourth layer N shell. Bohr's model of atom, 1913. Electrons revolve around the nucleus in stable orbits. Energy levels are shells without losing energy in the form of radiation. The orbit of energy levels are labeled KLMN, and K being the closest to the nucleus and N being the farthest. The ground state is the lowest energy level that an electron can occupy, typically referring to the electron's position in the K shell, the innermost shell. When an atom moves between different energy levels or shells, it either absorbs or emit energy. When an atom falls from a higher energy level to a lower one, it emits energy, usually in the form of electromagnetic radiation. When an electron moves from a lower energy level to a higher one, it absorbs energy. Distribution of electron. The maximum number of electron that can be presented in the nth shell is equal to 2n square. Thus, we have last shell or orbit, valence shell, electron, valence electron, shell, maximum number of electrons. First shell or K shell, n is equal to 1, that is 2 into 1 square 2. Second shell or L shell, n is equal to 2. 2 into 2 square is equal to 8. Third shell or M shell, n is equal to 3. 2 into 3 square is equal to 18. Fourth shell or N shell, n is equal to 4. 2 into 4 square is equal to 32. Discovery of electron, proton and neutron. Electron discovered by J. J. Thomson. Proton discovered by Rutherford and Goldstein. Neutron discovered by Chadwick 1932. In 1932, observed positive canal rays. Comparison of characteristics of electron, proton and neutron. Particle, charge of the particle, mass of the particle, symbol, location in the atom. Electron, minus 1 unit, minus 1.602 into 10 power minus 19 coulomb. Mass, 9.11 into 10 power minus 31 kg, that is 1 by 1840 unit. Symbol, 0 minus 1 power e. Location in the atom, outside the nucleus. Extra nuclear part, proton, plus 1 unit, plus 1 plus 1 point plus 1.602 into 10 power minus 19 coulomb. 1.673 into 10 power minus 27 kg 1 unit plus 1 p power 1 in the nucleus. Third, neutron, no charge, 1.675 into 10 power minus 27 kg 1 unit 1 n0 1 n naught in the nucleus, and both in the nucleus, both proton and neutron, 2000 approximately, that is approximately 1836 times more mass compared to electron. Neutron. Neutrons are subatomic particles that are formed in the nucleus of every atom, except for hydrogen, which only has proton in its nucleus. Protons and neutrons are collectively known as nucleons. The mass of a neutron is 1 atomic unit. Ions. The charged species are called ions. Negative charged ions are anion. Positive charged ions are cation. Positron, discovered in 1932 by Carl Anderson. Example: sodium chloride (NaCl) constitutes positive charged sodium plus sodium and negatively charged chlorine. Symbol are elements: hydrogen, azote, carbon, oxygen, phosphorus, sulfur, magnesia, lime, soda, aluminium, calcium, beryllium, silicon, yttrium, potassium, mercury, water, carbon dioxide, uh, carbonic oxide, strontium, barium, iron, zinc, copper, lead, silver, gold, platinum. Symbols were given by Berzelius for the first time. Dalton used it for the first time. Atomic number Z. Z is equal to number of proton. Number that is equal to number of electron. Z is equal to number of proton or number of electron. N is equal to nucleus is equal to proton plus neutron. Atomic number is always a whole number because they contains a whole number of protons, and an an atomic number of an element does not change during a chemical reaction. All atoms of the same element have the same number of protons in the nucleus, and hence have some atomic number. No two elements have the same atomic number. Mass number A. Mass number of an element A is equal to number of protons P plus number of neutrons N present in the atom of an element. Since protons and neutrons are present in the nucleus, these particles are collectively called nucleons. Thus, mass number of an element is equal to number of nucleons in the atom of that element. M, upper side n, small n, downside small p. Small n, mass number of protons plus neutrons, and small p, atomic number of protons. A is equal to small p plus small n. A is equal to capital Z plus small n. Capital A minus capital Z is equal to n. Protons Z plus is equal to 12. Electrons E minus is equal to 12. Neutrons N naught is equal to mass number minus protons P plus, that is equal to 12. Electronic configuration of first 20 elements. Hydrogen, electronic configuration 1. Helium, electronic configuration 2. Lithium, electronic configuration 2 1. Beryllium 2 2. Carbon 2 3. Beryllium, boron 2 3. Carbon 2 4. Nitrogen 2 5. Oxygen 2 6. Fluorine 2 7. Neon 2 8. Sodium 2 8 1. Magnesium 2 8 2. Aluminium 2 8 3. Silicon 2 8 4. Phosphorus 2 8 5. Sulfur 2 8 6. Chlorine 2 8 7. Argon 2 8 8. Potassium 2 8 8 1. Calcium 2 8 8 2. Question: an ion M3 plus 3 electrons loss. It contains electrons 10, neutron 14, A question mark Z question mark. What is the A and Z of the element? Z is equal to 13. A is equal to P plus N. That is 13 plus 14. A is equal to 27. Isotopes. Isotopes are atoms of same element which has the same atomic number but different mass number. Isotope of an element differ only in number of protons present in the nucleus. Isotopes of hydrogen: 1h1, electron is equal to proton is equal to 1, neutron 0, it is protium. 1h2, electron is equal to proton is equal to 1 and neutron is equal to 1, deuterium. 1h3, electron protons are 1 1 each and neutrons are 2, tritium, radioactive in nature. Hydrogen 1, mass number 1, hydrogen 2, deuterium, mass number 2, hydrogen 3, tritium, mass number 3. These three are isotopes of hydrogen. Proton, electron in hydrogen 1, proton, neutron, electron in hydrogen 2, proton, neutron, electron in hydrogen 3. Isotopes of carbon: uh, C 12 C6, 12 C6, electrons and protons 6, neutrons 6, and 13 C6, electrons, protons 6 and neutrons 7. 14 C6, electrons, protons 6, neutrons 8. Used in carbon dating. Age of fossil and used in carbon dating. Age of fossils and other things. Carbon 12, 6 protons, 6 neutrons. Carbon 13, 7 protons, 6 neutrons. Carbon 14, 8 protons, 6 neutrons. Characteristics of isotope: same chemical properties, same electronic configuration, so same number of valence electrons. Since chemical property depends upon the number of valence electrons, therefore they have same chemical properties. Different physical properties. Since the isotopes of an element have different masses, different physical properties like melting point, boiling point, density, etc. exist. Atomic mass number of chlorine is equal to 35.5. 35 Cl17 and 35 Cl17 in 3 is to 1 and 37 Cl17. 35 Cl17 and 37 Cl17 in 3 is to 1 ratio. Atomic mass is equal to 35 into 3 plus 37 plus 1 by 3 plus 1, 35.5. Use of isotopes. Use in a nuclear reactor, uranium 235. Used in a radiation therapy to prevent cancer, cobalt 60. Used in a treatment of goitre, iodine 135. Isobars. They are atoms of different chemical elements that have same mass number but different atomic numbers. Isobars and their properties. They are atoms of different elements. They have different atomic number. They have same mass number. They have similar physical properties and different chemical properties. They have different number of protons, electrons, neutrons. Example: 40 argon 18, 40 potassium 19, 40 calcium 20, and 40 argon 18 is 18 protons, 22 neutrons, and 18 electrons. 40 potassium 19 is 19 protons, 21 neutrons, 19 electrons, and 40 calcium 20 is 20 protons, 20 neutrons, and 20 electrons. Isotone. They have same number of neutrons. Element: proton, neutron, and electron. 60 oxygen 8. 8, 8, 8 proton, neutron, electrons are same and are equal. 15 nitrogen 7. 7 proton, 7 electron, and 8 neutron. Neutrons are same, 8, 8 in oxygen and nitrogen. Atomicity. The total number of atoms that make up a molecule of an element. Element atomicity. Argon monoatomic 1, helium monoatomic, oxygen diatomic 2, hydrogen diatomic, nitrogen diatomic, chlorine diatomic, phosphorus tetraatomic 4, sulfur polyatomic more than 3. Mole concept: Avogadro number 6.022 into 10 power 23 is equal to 1 mole. Number of moles is equal to given mass small m by molecular mass capital M, that is equal to given number of particles capital N by Avogadro number n naught. Small n is equal to small m by capital M, that is equal to n by capital N by n naught. One molecule of copper is equal to 63.5 grams. Calcium atom mass 12. 1 mole of copper is equal to 63.5 grams, and copper atom mass 63.5, and 6.02 into 10 power 23 atoms. It is Avogadro number. What will be the number of molecules in 2 grams of helium? N is equal to 2 by 4, that is equal to 1 by 2, that is 0.5 moles. Number of moles in 12.044 into 10 particles of nitrogen atom. Small n is equal to 12.044 into 10 power 24 by 6.022 into 10 power 23, that is equal to 20 moles.